Welcome to the deep dive. Today we're diving headfirst into a topic that, well, for many, still feels like it's shrouded in this persistent cloud of confusion. Deep learning and AI. Even for those of us immersed in technology, really getting a handle on its intricacies can be tricky, almost like trying to catch smoke sometimes. There's this tendency, especially in public conversations, to frame it in almost mystical terms, often, packed with hype, and frankly, that creates a sense of something fundamentally inaccessible, like it's only for a select few. And the most frustrating part for me, the pervasive use of the black box analogy. While it might seem like a convenient shorthand, it's not just inadequate, it's, in my view, actively misleading. It suggests these systems are inherently opaque, maybe impossible to understand, which honestly does a disservice to the considerable algorithmic ingenuity embedded within them. Accepting that black box label actually discourages deeper inquiry, and it fundamentally misrepresents their technical nature. Because while they are incredibly complex, they are absolutely not magical. They are rigorously engineered systems. So our mission today is clear.
We were moving decisively beyond those oversimplifications, those mystifications. We're going to confront the core technical substance of deep learning head-on. Our objective is to provide you with a detailed, technically grounded, and hopefully genuinely accessible breakdown of its fundamental workings. We'll focus explicitly on the underlying algorithms, the architectures, the methodologies that make it all tick. We promise to minimize jargon where possible, maximize clarity in every technical explanation. Let's unpack this.
That's exactly right. We're going inside. Let's begin with section 1. Building the brain, pre-training labyrinth construction. So we're starting with the foundational step, how these massive models consume and process information during their initial intensive learning phase. We call this pre-training. Think of it as the ultimate data feast for the model. 1.1 data feed, the big data load. Okay, the first thing that really hits you about deep learning models, especially these incredibly large language models, is their, insatiable hunger for data. They need to consume an absolutely enormous, almost elephant-like amount of information just to function effectively. And what kind of fuel powers these AI brains? Primarily text data, drawn from virtually every corner of the digital world, even the physical world sometimes. We call these vast collections corpora, which is just a fancy term for a massive collection of text, and it's undeniably heterogeneous.
Heterogeneous meaning just mixed sources.
Exactly. A diverse mix from countless different sources, all blended together. We're talking text pulled from the immense expanses of the internet, colossal archives like Wikipedia, countless news articles, personal blogs, vibrant online forums, even user-generated content from platforms like Reddit.
Okay, so basically the internet's text.
Pretty much. Plus books, literally libraries upon libraries of scanned books. Everything imaginable, from classic novels to incredibly dense technical manuals, and perhaps surprisingly, even computer code. Languages like Python, Java, C++, many others, all thrown into this mix.
So too. Interesting.
Yeah, it's truly an untamed data salad, as some call it. And as you might expect, with such a broad, uncurated collection, it comes with plenty of noise, potentially some bad information, and definitely various biases reflecting the human world it's drawn from.
Right, it learns from our mess, essentially.
Yeah, precisely. Yet, remarkably, the model is designed to learn from all of this messy, raw data. This raw data becomes the fundamental material, the pure energy for the machine learning process, and the sheer volume needed is colossal. We are talking petabyte scale volumes, realistically.
It's a lot of hard drives.
It really is. It gives you a real appreciation for why data centers are expanding at such a dizzying pace. You realize how quickly hard disk space just vanishes when you're working at this scale. It's quite something to witness firsthand. I've personally seen setups where engineers are physically struggling to find enough high-speed NVMe connectors for all the storage needed.
Wow. Okay, so you have this mountain of raw text. What happens next? How does the machine even start to process it?
Right. So after we gather this immense load of raw text data, which is essentially endless strings of words, we face a fundamental challenge. A machine cannot directly understand words as we write them. At its core, a machine fundamentally only understands numbers.
Zeros and ones, basically.
Well, numbers in general. So the first and absolutely critical step is converting these words into numerical representations. This conversion process is what we call tokenization. It's essentially an algorithm, a clever set of instructions, specifically designed to break down that raw, continuous text into smaller, more manageable pieces. We call these pieces tokens. Typically, tokens represent individual words or sometimes even just meaningful parts of words.
Okay, so breaking sentences into word-sized chunks, more or less.
That's the simplest approach, yeah. Just split the text wherever you find spaces, commas, periods, any punctuation. That gives you individual words, roughly. But in practice, it's rarely that simple.
Mm-hmm.
A more nuanced, more intelligent approach is often needed.
Like what? What's an example?
Well, take the word don't. Should you treat it as one single token, don't? Or split it into two distinct tokens, do and int?
Ah, I see. That matters for meaning.
It does. The tokenization algorithm itself needs to make these kinds of sophisticated decisions based on patterns it observes in the language data. That's precisely why advanced algorithms like byte pair encoding or BPE are very common in practice.
BPE, how did that work?
BPE starts by treating individual characters as its base units. Then, it iteratively looks for common pairs of characters that frequently occur together in the data. Once it finds them, it groups these common pairs into new, longer tokens. This process repeats, continuously creating longer tokens based on what patterns are statistically most common in the training data itself.
So it learns the common word parts from the data.
Exactly. WordPiece is another algorithm conceptually quite similar, slightly different approach to identifying tokens, but the same core idea, breaking words into meaningful subunits. And then there's sentence piece, which offers even more fine-grained control by breaking text into subword units, sometimes even smaller than whole words, allows for like universal tokenization regardless of the input language.
Why all this complexity? Why not just split by spaces?
Good question. Several reasons. First, it handles different forms of words like run, running, ran more effectively, and rare words too. Second, it drastically improves efficiency by reducing the overall size of the vocabulary the model needs to manage. Fewer unique tokens.
Right, instead of storing every single word ever written.
Exactly. And crucially, it allows the system to gracefully deal with words it's never seen before during training. Unknown words.
Oh.
By intelligently breaking these unknown words into smaller, recognized pieces, the subword tokens, it does know the model can still process them meaningfully. So what starts as a complete chaos of raw text finally gets transformed into an ordered, structured list of tokens. And these tokens, behind the scenes, are actually precise numerical representations now. We transform the untamed chaos into ordered, manageable shards of information.
Okay, so we have tokens, which are numbers representing words or parts of words. But as you highlighted, at this stage, they're really just index numbers, like word number 5, word number 87, right?
Yeah.
That's simply not enough for a machine to truly understand anything meaningful beyond just recognizing a word's index.
Exactly. It's just an ID.
So, to give the machine much more information about each word, we need to embed these words into what's called a vector space. What this means is that each word doesn't just get a simple index number. It transforms into a vector, which is essentially a long, structured list of numbers.
A very long list.
Right, long, hundreds, even thousands of numbers. We call these high-dimensional vectors, or more commonly in deep learning, embeddings. Think of it like this. For each word, we create a kind of unique numerical fingerprint.
That's a good analogy, a fingerprint.
And this fingerprint, this vector, isn't just random numbers. It aims to capture the deep meaning of that specific word. And critically, it also captures how that word relates to all sorts of other words in our language.
Yeah, the context, the semantics.
So the core idea is that words with very similar meanings, like, say, cat and dog, will have their numerical fingerprints, their vectors, positioned quite close to each other in this space. On the other hand, a word with a very different meaning, like car, will have its vector much further away from cat and dog.
Geometrically speaking, yes. Closer in space means closer in meaning.
Now, it's really important to grasp that this vector space isn't a simple 3D space we can easily picture in our heads. No, it's a hyperdimensional space, which means it has many, many dimensions. Imagine a space with maybe hundreds, maybe 500 dimensions, for instance.
Yeah, impossible for us to visualize directly.
Incredibly difficult for a human brain to actually imagine. But for the machine, no problem at all. Machines operate very effectively within these high-dimensional spaces.
They crunch the numbers just fine.
So how do we create these embedding spaces? We don't design them manually. Right?
Yeah, definitely not. Powerful algorithms learn to create these embedding spaces automatically, directly from that massive big data we discussed. Essentially, by seeing words appearing in context over and over again, across billions of examples in all that data, the machine statistically figures out which words tend to appear in similar contexts. It learns which words are often related, which words have opposite meanings. Based on all these complex statistical relationships it finds, it automatically positions them in the right places within this incredibly complex hyperdimensional space.
So it learns proximity means similarity, just by seeing how words are used.
That's the core idea. Words are effectively projected into this numerical space, these embedding spaces. Their complex meanings and intricate relationships get encoded right there within the numerical structure.
And once this embedding process is done, that's when the machine genuinely starts to gain something approaching a basic understanding of words. It moves beyond simple keyword matching to grasp the nuance.
Precisely. It's the foundation for deeper understanding. Okay, so let's move on. Section 1.2, Architecture. The transformer model many layers deep. So after tokenization and embedding, we have these precise numerical word representations, these vectors. Now we need an architecture, a kind of computational blueprint to truly process them and extract meaningful patterns. The transformer model is the dominant one here. It's a remarkably deep network, structured almost like a very tall building made of many stacked layers of complex calculation.
Okay, like a skyscraper of math.
Kind of, yeah. And inside each of these layers are the crucial components that unlock its extraordinary power. When you look inside each transformer layer, if you ask what is the single most important part, the innovation that truly makes the transformer architecture so incredibly powerful, it's undoubtedly the self-attention mechanism.
Self-attention. Heard that term a lot.
It's the real game changer, the core, clever idea that revolutionized natural language processing. The basic concept is elegantly simple, really. When the model is processing any one specific word in the input, it absolutely needs to actively look at all the other words present in that same input. Why? To properly understand the full context around that word. It can't just process words in isolation.
Right, context is everything in language.
Exactly. Its strength comes from seeing clearly how all these words relate to each other within the current sentence, the paragraph, maybe even the whole document. And self-attention is precisely what enables the model to do this with remarkable efficiency.
And this was a big deal compared to older models.
Huge deal. Previous models, like RNNs, often struggled with long-range dependencies. They kind of forget the beginning of a long sentence by the time they reach the end. Self-attention broke that barrier. It lets every word instantly see and relate to any other word, no matter how far apart. That allows for truly nuanced understanding of complex language. Think about understanding sarcasm or irony that often relies on distant context. Self-attention makes that feasible for an AI.
Okay, makes sense. So how does it do that? How does it look at other words?
All right, let's get into it. For every single word, or more accurately, every single token in the input sequence, the algorithm dynamically calculates how much attention it should pay to all other words. It does this using special vector representations called query, key, and value vectors.
Query, key, value, QKV.
Exactly. Remember those embedding vectors we just discussed? We take the embedding vector for each word and then use learned linear transformations, just matrices of numbers tuned during training, to create these three new vectors from each embedding. So for every word, you now have a unique query vector, a corresponding key vector, and a value vector.
Okay, 3 vectors per word derived from the embedding. Then what?
Then the critical calculation begins. For each individual word, the algorithm takes its query vector and directly compares it mathematically with the key vectors of all the other words in the same input sequence, including itself.
Comparing query to all keys. How?
Using a mathematical operation called a dot product, this tells us how aligned or similar the query of one word is to the key of another. High dot product means high relevance, basically. These raw dot product values are then typically scaled down a bit, just to stabilize the calculations. Then we apply a softmax function.
Softmax. That turns things into probabilities.
Exactly. This function transforms these raw comparison values into clear attention weights probabilities that sum to 1. They show precisely how much attention this word should pay to every other word. So if the attention weight is high for word X relative to our current word, it means word X is mathematically determined to be especially important for understanding the current word being processed.
Okay, so the weights tell it where to focus.
Precisely. Finally, once we have all these attention weights for a given word, these weights are used mathematically again to weight the corresponding value vectors of all those other words. And then these weighted value vectors are all summed up together.
Summing the weighted values. What does that give you?
The final result, after this whole sophisticated process, is what we call a context-aware representation, specifically created just for this current word that started the calculation. It's like the original word's meaning, but now enriched by the context from all the other relevant words.
Wow. Okay, that's intricate.
It is. And this entire process creating Q, K, V vectors, the dot product comparisons, softmax for weights, weighting and summing the value vectors, all of that together is what self-attention truly means technically. It is the main calculation unit, the heart and soul of the transformer architecture.
And it's self-attention because the sequence is attending to itself.
Exactly. Each word, mathematically, attends both to itself and to all the other words within that same input sequence internally, checking statistical relevance, contextual dependency, all those connections. This is fundamentally why transformers are so remarkably good at understanding, processing, and generating natural human language context.
Okay, self-attention is the core. Is that all that happens in a transformer layer?
Not quite. After this powerful self-attention calculation is done for all the words within a layer, there's usually another important processing step, what we call the feed-forward network, or FFN.
FFN, another network inside the layer.
Yep. Think of it as an extra processing layer, an additional calculation step systematically applied to each word representation after self-attention has done its work. The feed-forward network itself, at a basic level, is essentially a smaller neural network embedded within each transformer layer. Often quite straightforward, typically two main linear layers with a crucial nonlinear activation function like RLU or GLU slotted in between.
RLU or GLU.
Those just add nonlinearity, right? Help it learn complex patterns. Exactly. And this feed-forward network, importantly, is applied separately and position-wise, as we say technically, to every individual word vector.
Position-wise, meaning each word goes through it independently.
Correct. Every single word vector that emerges from the self-attention calculation then gets processed independently through this exact same feed-forward network structure.
What's its purpose then, if self-attention already figured out the context?
Good question. The primary aim is to add even more complexity and, crucially, inject further nonlinearity into the model's computations at each step. This additional processing allows the transformer model at each layer to learn even more intricate transformations of the word representations, going beyond what's directly captured purely by self-attention.
So attention finds the relationships, and the FFN processes each word based on those relationships.
That's a great way to put it. While self-attention brilliantly finds and captures dependencies between words, the feed-forward network, in my view, helps to further refine each word representation independently, but crucially, already informed by those relationships. It's almost like attention figures out who is related to whom, and then the FFN processes each who in detail, informed by that relational info. You could say it adds depth after breadth.
Depth after breadth. I like that. So it's essential, too.
Absolutely. Essential for the model's overall power and expressiveness, working hand in hand with attention in each layer.
Okay, so we're building these incredibly deep networks, many layers stacked up. You mentioned transformer layers. We're talking dozens, hundreds?
It varies, but yeah, large models can have many dozens of these layers stacked, 48, 96, even more sometimes.
Wow, okay, but here's where it gets really interesting and maybe challenging. These very deep networks are surprisingly hard to train in practice, aren't they?
Oh, definitely. That's a huge engineering challenge.
One of the biggest problems I've read about is the vanishing gradients problem. Can you explain that?
Sure. Essentially, as the error signal, which is vital for learning, tries to flow all the way back through layer after layer during training, the gradient signal, which tells each part of the network how to adjust, tends to become progressively very, very small. Tiny, really.
Especially for the early layers, right? The ones near the input.
Exactly. As it propagates backwards towards those earlier layers, the practical problem is that these early layers, because they receive such a weak, vanishingly small gradient signal, they just don't get updated properly. Or at all.
And if the first layers don't learn, the whole thing breaks down.
Pretty much. The training of the entire deep network becomes exceedingly slow and, quite frustratingly, effectively stalls, almost completely sometimes.
Okay, that's vanishing gradients. But you can also get the opposite, exploding gradients.
Right. To add to the fun, sometimes the gradient signals, rather than vanishing, dynamically become far too large. They explode numerically.
And that makes training unstable.
Deeply unstable. Frequently, you'll find it just doesn't properly converge towards any meaningful minimum error level whatsoever. The numbers just fly off the charts.
So how do we deal with these? How do we train these super deep networks reliably?
Thankfully, there are two extremely valuable, really crucial techniques that are completely essential for properly training deep transformer networks: residual connections and layer normalization.
Residual connections, also called skip connections?
That's right, skip connections. The underlying idea itself is actually remarkably simple, almost elegant. It's basically to systematically take the input of one specific layer and just directly add it, as it is, completely unmodified, straight through to the final output of a few subsequent layers further along.
Like creating a shortcut.
Exactly, an informational shortcut through the layers. This very simple but very clever idea brilliantly allows the crucial gradient signals to then flow far more easily and directly through the deep network. It fundamentally bypasses many of the computationally complex intervening layers, at least for the gradient flow.
Ah, so the gradient doesn't have to go through every single transformation. It can take the shortcut back.
Precisely. By directly bypassing layers in this structured way, you systematically avoid, or at least dramatically mitigate, the otherwise extremely prevalent vanishing gradients problem.
And does it help in other ways too?
Yes, a genuinely beneficial side effect. This informational shortcut also helps very valuable original information content to consistently flow more directly across successive layers. This demonstrably helps with consistently and robustly training much deeper neural networks than we could ever really achieve effectively without them, especially at scale.
Okay, so residual connections help gradients flow. What about layer normalization? How is that different?
Layer normalization, while related in aiming to solve gradient stability issues, its underlying mechanism is subtly but importantly different. Layer norm ensures that as signals pass through each layer, they remain in a predictable range, not too strong, not too weak.
Like keeping the volume consistent.
That's a good way to think about it. Like having a volume knob for each layer, constantly adjusting so the signal is clear and consistent. This keeps the training process stable and speeds up learning. The practical issue in deep networks is that raw neuron activations can dynamically become extremely large sometimes, or conversely, almost vanishingly small. It depends dynamically on the shifting input patterns and changing network parameters during training.
So layer norm fixes that.
Yes, layer normalization addresses this inherent issue. It methodically rescales and then precisely shifts all the neuron activations dynamically generated within each specific layer. It basically keeps the activation centered around 0 with a standard deviation of 1, statistically speaking.
And this helps training how?
This continuous dynamic normalization across the network has several very demonstrably positive effects in practice. It quite significantly helps make overall training much more stable. Practically, it helps lead to much faster training convergence. Empirically, we see substantially sped up convergence time compared to training without it.
Faster training is always good.
Always. And surprisingly, it can also demonstrably help improve the final trained model's ultimate generalization performance. That is, how well the trained model works in deployment on genuinely new, unseen data.
So better performance on real-world tasks too.
Often, yes. In my experience and from everything I've seen, both residual connections and layer normalization are undeniably absolutely essential ingredients if you genuinely want to systematically and reliably train very, very deep transformer networks.
So without them, it's basically impossible.
Honestly, without a methodical strategy for tackling gradient problems and stabilizing activations throughout the considerable depth, effective, reliable training of these deep models, especially transformers, realistically, it just practically becomes, if you ask me, genuinely impossible, or at the very, very least, functionally very, very difficult. They're non-negotiable for deep learning today.
All right, let's move to the next part, section 1.3. Pre-training goals, making model learn language basics. Okay, so once a transformer architecture is built, you've got your layers, your attention, your FFNs, your skip connections, your layer norm, and the data is ready. The next step is to actually train it, to make it learn something meaningful from all this data. The first big step, pre-training, is like the model going to language school.
Language school, I like that.
Yeah, learns grammar, vocabulary, sentence structure just from reading lots and lots of text. But crucially, without anyone directly telling it this is correct grammar or this is a noun.
That's unsupervised learning, right? Learning patterns from the data itself. Exactly, unsupervised learning. And there are a couple of key tasks models use for this. One really important pre-training task is masked language modeling, or MLM. Think of it like a complex fill-in-the-blanks game.
Fill in the blanks. How does that work?
You take a sentence, you hide some words by replacing them with a special mask token, and then you ask the model to guess what those missing words were, based only on the rest of the sentence, the surrounding context.
Okay, like the cat sat on the mask.
Precisely. The model has to predict map. Technically, we randomly mask about, say, 15% of the words in the input sentence. The model's output is a probabilistic prediction, its best guess for what those masked words most likely originally were.
And how does it learn to guess right?
We use a loss function. We talked about loss before. It's like a report card. It gives a number telling us how wrong the model's predictions are compared to the actual word that was masked.
The goal being to minimize that loss number.
Always get it as close to zero as possible. For MLM, we typically use cross-entropy loss, which specifically measures the difference between the model's predicted probabilities for words and the actual correct word.
So by trying to get better at this game.
Exactly. By systematically performing this task again and again for literally millions and billions of sentences from that massive data set, it effectively forces the model to learn genuinely important things about language structure. It has to learn to understand words, their nuanced meanings, complex relationships between words, how they're commonly used. Basic grammar, crucially, also gets implicitly learned.
Because you can't guess the missing word without understanding the sentence structure.
Precisely. To reliably guess the masked word correctly, the model needs to effectively understand the surrounding sentence structure and context right there from scratch. The MLM task, when you really get down to it, is like a complex fill-in-the-blanks challenge at scale, but it's also demonstrably a surprisingly and remarkably powerful way to effectively pre-train core underlying language understanding directly into the model, systematically from the data upwards.
Okay, MLM is one way. What's another pre-training task?
Another key one is causal language modeling, or CLM. This is different from MLM in a crucial way. CLM learns to predict the very next word in a sequence. Think of it like continuously writing, always predicting what should come next.
So if the input is the quick brown fox, the model predicts jumps.
Exactly. Then if the input is the quick brown fox jumps, it predicts the next word after that, say over, and so on, predicting one word at a time sequentially.
And it's causal because...
Because the prediction for any given word only uses the words that came before it in the sequence. It can't peek ahead to see future context, unlike MLM, which sees context on both sides of the mask.
Right, just like how we speak or write, one word after another.
Exactly. For CLM, we typically use the transformer decoder architecture. The input is simply a word sequence, and the model predicts probabilities for the next word. Again, we use cross-entropy loss to measure how accurate its next word predictions are. It's trained on huge amounts of text.
And what does this teach the model?
By constantly doing this next word prediction, the model learns not just words, but how to generate coherent text, how to construct sentences with proper grammar, even how to adopt specific writing styles it sees in the data. It's learning how to continue a thought, tell a story, provide a natural-sounding response. To predict the next word well in real text, the model must understand these basics of language flow and structure.
So CLM is more about generation, while MLM is more about understanding context.
That's a good way to think about it, broadly speaking. CLM is like playing predict the next word repeatedly, and it trains the model to create text that sounds natural and follows the intricate patterns of human language. Both are crucial pre-training steps.
Okay, that makes sense. Pre-training gives it general language skills.
Yeah.
But that's not the end of the story, right? Section 2, task-specific tuning, fine-tuning for specific jobs. Pre-training, as we've explained, teaches the model core language abilities. Undeniably true. But it leaves the model in a state that's still primarily generally capable. Think of it like you've got a perfectly good blank notepad. It's excellent for writing text in general, certainly, but it's fundamentally not yet specialized or precisely honed for any specific actual real-world task. You see my point?
Absolutely. It knows language, but it doesn't know what job you want it to do yet.
Exactly. To actually make these models genuinely, demonstrably, practically useful in specific ways, like diligently answering specific user questions, efficiently generating concise summaries, or reliably engaging in realistic conversations, well, then we absolutely need another clearly distinct and crucially important subsequent training phase.
Fine-tuning.
Exactly, fine-tuning. This phase always follows right after that initial broad pre-training work is done, and is precisely where we rigorously train the already pre-trained generalist model again. But importantly now, it's exclusively for a highly focused, explicitly predefined, very narrow set of practical end-user tasks that we as engineers actively intend the model to reliably deliver.
Right. Making it useful for something specific.
And I must stress, for this entire subsequent targeted fine-tuning phase, we methodically rely consistently and it's essentially almost exclusively on supervised learning techniques.
Giving it examples of the specific task.
Exactly. Input-output pairs. Those supervised techniques remain the foundational training approach used almost universally in practical large language model deployments for specialization.
When I approach fine-tuning a model using supervised learning, I treat it as a structured process. It's similar to pre-training in mechanics, but with very specific targeted data sets and clear goals for each task. Let's use a question answering task as an example. I define the input as the question text provided by a user and the desired output as the correct answer text.
So you have pairs of questions and their ideal answers.
Precisely. I feed the question into the model, which generates an answer based on its current knowledge. Then, I meticulously compare its generated answer to the correct answer from my prepared dataset. These are the human-verified ideal responses I've curated beforehand.
And again, you've used a loss function.
Yep. To quantify how well the model is doing, I use a loss function, typically class entropy loss again, which measures the numerical difference between the model's output and that correct target answer. My primary goal during this fine-tuning phase is to minimize this difference as much as possible. Make the model's predictions as close to the correct answers as it can get for this specific task.
And how do you adjust the model to get better?
We rely on that foundational algorithm called backpropagation. Remember how we discussed gradients flowing backward?
Yeah, the error signal tells the network how to change.
Exactly. Backpropagation sends the error signal that loss we just calculated backwards through the entire network, layer by layer. It meticulously tells each connection and parameter in the network exactly how much it contributed to the mistake, and therefore how it needs to adjust its numerical value slightly to do better next time. This is how the model's parameters, its internal weights and biases, are precisely adjusted during fine-tuning.
And you do this over and over.
Yes, I repeat this iterative process for all examples in the specific task dataset, cycling through the entire dataset many times over multiple epochs. With each epoch, the model gradually learns to map the specific inputs, like questions, to the precise desired outputs, like answers, by observing these right answer examples.
And the same process applies to other tasks like summarization or translation.
Exactly the same fundamental method. Define the input, establish the target output, calculate the loss based on the difference, and meticulously update the parameters using backpropagation. This iterative process is how we guide a generally pre-trained model to specialize and excel in specific real-world tasks through supervised fine-tuning.
Okay, that makes sense. Fine-tuning adapts the general model, but the core of both pre-training and fine-tuning involves adjusting those parameters based on loss. Let's talk more about that adjustment process. Section 2.2. Optimization techniques, getting parameters to correct values. When we train neural networks, whether it's that massive pre-training or the specialized fine-tuning, the entire process fundamentally revolves around optimization. We have that loss function, which tells us how poorly the model is performing. Our absolute goal is to minimize that loss, get that number down.
Find the lowest point in the loss landscape.
Exactly. To achieve this, we systematically adjust the model's parameters, its weights and biases, using optimization algorithms. One of the most basic and widely used is stochastic gradient descent, or SGD. To picture this, I often imagine the loss function as this vast, complex surface in a high-dimensional space, like a landscape of mountains and valleys.
Yeah, very bumpy landscape usually.
Right. Our model's parameters represent our current position on this surface. Our objective is always to find the lowest point, the deepest valley floor where the loss is minimized. The gradient of the loss function at any given point tells us the direction of steepest descent, essentially the fastest way downhill on that landscape.
Follow the slope downwards.
Exactly. SGD follows this gradient direction in small, controlled steps, gradually moving towards that minimum loss. It's called stochastic because instead of calculating the gradient across the entire massive data set at once, which would be computationally insane.
Totally impractical for large data sets.
Right. We calculate it on small batches of data instead. This approach is much faster, though maybe a bit noisier.
Yeah, the gradients from each small batch might not perfectly point downhill for the whole data set, but on average, they do.
So, over many steps, the overall direction remains correct, consistently guiding the model closer to the minimum loss. A critical parameter here is the learning rate.
Ah, yes, the learning rate. Crucial.
It determines how large each step should be, right? How far you jump downhill each time.
Exactly. And getting it right is tricky.
If the learning rate is too high, the model might dramatically overshoot the minimum, bounce around, maybe never settle down.
Yep. Overshoot and diverge.
But if the learning rate is too low, training becomes agonizingly slow. Tiny little steps take forever.
Painfully slow. So you need a balance.
To strike that balance, we often use sophisticated learning rate schedules, like starting faster and slowing down.
Very common. Start with a higher learning rate for big initial progress, then gradually reduce it as you get closer to the minimum to fine-tune the landing. It helps ensure efficient and stable training. SGD is fundamental, but for the scale and complexity of modern deep learning models, we often move to improved adaptive optimizers. Things like ADAM, ADAM-W, AdaGrad, RMS-prop. There are quite a few.
Adaptive optimizers. What makes them different from basic SGD?
The key difference is that adaptive optimizers automatically adjust the learning rate for each parameter individually and over time.
Whoa! So instead of one learning rate for the whole model, each connection gets its own, potentially.
Effectively, yes. It adapts the step size based on the history of gradients for that specific parameter. This is a crucial difference from basic SGD, which uses a single, usually decaying learning rate for everything.
And ADAM is a popular one.
Very popular, yes. Adam cleverly combines two concepts, momentum and Armstrong.
Okay, what's momentum in this context?
I think of momentum like a ball rolling downhill. If it has momentum, it keeps rolling even if the slope temporarily flattens or bumps slightly upward. It helps it power through small obstacles or shallow valleys.
So it avoids getting stuck easily.
Exactly. In the optimizer, momentum uses information from past gradients to inform the current update direction, rather than relying solely on the immediate current gradient. It smooths out the path. This technique significantly speeds up training and helps the model navigate complex loss landscapes, overcoming oscillations, or avoiding being trapped in suboptimal local minima.
Makes sense. And RM's prop, what does that add?
RMSprop adjusts the learning rate based on the average of recent squared gradients. For parameters that have consistently large gradients, the learning rate for that specific parameter is automatically reduced. While for parameters with smaller gradients, it can be increased. It adapts the learning rate based on how much that parameter has been changing recently.
So it automatically tunes the step size for each parameter.
That's the idea. This adaptive approach helps improve convergent stability and accelerates training, particularly for parameters that might be otherwise difficult to optimize consistently.
And ADAM-W, just a variation.
ADAM-W is a widely used variation of ADAM. It includes an improved implementation of weight decay.
Weight decay, that's for regularization, right? Preventing overfitting.
Exactly. Weight decay is a regularization technique that helps prevent the model from fitting the training data too perfectly, ensuring it generalizes better to new, unseen information. ADAM-W handles this regularization slightly differently and often more effectively than the original ADAM.
So using these adaptive optimizers like ADAM-W generally leads to faster training, better results.
Generally, yes. Much faster convergence and demonstrably better performance, especially when training the very large and complex neural networks we see today.
But people are still researching new optimizers.
Oh, absolutely. The research into optimizer algorithms is incredibly dynamic. We're always on the lookout for new ways to make training these massive networks even more efficient and effective. It's a constant area of innovation.
Okay, fascinating. So we've covered pre-training, fine-tuning with supervised learning, and the optimization algorithms that drive it all. But there's another layer, right? Especially for models that interact with humans. Section 3, Guiding the Behavior Reinforcement. Learning from Human Feedback, or RLHF. Making model useful and helpful. When we use supervised fine-tuning to make a model good at specific tasks, like answering questions, we quickly learn something important. Being correct isn't always enough for real-world use.
Yeah, correctness and usefulness aren't always the same thing.
Exactly. We also want the model to exhibit a range of desirable behaviors. We want it to be helpful, to be harmless, to be truthful, and crucially, to be aligned with human values. Supervised training on datasets alone often isn't enough to achieve this deep alignment, because a model can still generate answers that are technically accurate but may be unhelpful, biased, toxic, or just weird.
Right. The supervised data might not capture those nuances of helpfulness or harmlessness perfectly.
So to address this crucial gap, we rely on a sophisticated training stage called Reinforcement Learning from Human Feedback, or RLHF.
RLHF, the key step for alignment.
Yes, in RLHF, we use human judgments directly to guide the model's behavior and make it more aligned with what people actually want and prefer. The first critical step in RLHF is collecting what we call human preference data.
Getting humans in the loop.
Exactly. We do this by asking human raters to compare different outputs generated by the model and tell us, quite simply, which one is better. For example, we might give the model a question. It generates two different answers, say answer A and answer B. We show both to a human rater and ask, from a user's perspective, which answer do you prefer?
And these raters have guidelines.
Absolutely. Raters are meticulously trained to judge based on specific criteria. What makes a good answer in this context? Helpfulness. Does the answer truly address the question, provide genuine value? Truthfulness. Is it factually accurate, not made up? Harmlessness. Is it safe, non-toxic, not offensive, doesn't promote harmful ideas? And maybe politeness. Is the tone respectful?
So, judging multiple dimensions of quality.
Right. Depending on the specific application, different RLHF setups might prioritize different criteria. Raters typically provide feedback as explicit rankings, like A is clearly better than B, or they might assign numerical scores, say from 1 to 7, for different aspects.
So you end up with a data set of preferences, A, B, C, D, etc.
Exactly. This human feedback is invaluable because it directly reflects what real users genuinely prefer, capturing nuances hard to encode in traditional data sets. However, it's a labor-intensive and costly process, right? Having humans read all these outputs.
Extremely. That's the bottleneck, which is why we need to use this valuable feedback as effectively as possible. So once we collect this crucial human preference data, A, B, C, D, we use it to train the model, but as you said, not in the standard supervised way. Because human feedback isn't a single right answer. It represents a preference, a relative comparison.
Right. So how do you train with preferences?
To effectively incorporate this type of data, we first train a specialized component called a reward model.
A reward model. Okay, what's that?
The reward model is a separate neural network, often a smaller transformer model compared to the main language model, but still quite capable. Its core job is to learn to predict human preferences.
So it learns to think like the human raters.
Essentially, yes. We feed the reward model inputs, which are the outputs generated by the main language model, like answer A or answer B. The reward model then processes these inputs and generates a single numerical output, a reward score. A higher reward score indicates that humans are more likely to prefer that particular output.
And how do you train this reward model?
We used the human preference data we collected. For each pair of outputs that humans compared, say A and B, where the human judged A to be better, we trained the reward model to assign a higher numerical score to A and a lower score to B. We use a specific loss function designed to encourage the reward model to align precisely with these known human preferences. Maximize the difference in scores for preferred versus non-preferred answers.
Okay, so the reward model learns to mimic the human judgments.
Exactly. After this training, the reward model gains a remarkable ability. It can automatically evaluate the quality of the main language model's outputs and assign a reward score, essentially acting like a human rater, but doing it instantaneously and at scale.
Ah, so you replace the slow human rating with this fast reward model.
Precisely. The key advantage is profound. The reward model becomes, in essence, an automatic predictor of human preferences. This is crucial because we can now use this automated reward signal to guide the subsequent training of the main language model using reinforcement learning, consistently pushing its outputs to be more aligned with what humans genuinely want, as predicted by the reward model.
Okay, this makes sense. You train a judge, the reward model, based on human examples, then use that judge to train the main model. Section 3.2, reinforcement learning loop, using human feedback to tune the model policy. Now that we have the reward model, which can effectively judge outputs based on human preferences, we can use its reward signal to fine-tune the main language model through reinforcement learning. Our ultimate goal here is to train the language model to consistently generate outputs that receive high reward scores from the specially trained reward model.
Because high scores mean humans are likely to prefer those outputs.
Exactly. The reinforcement learning algorithm we typically use for this is Proximal Policy Optimization, or PPO.
PPO, another key acronym?
Yep. PPO is ingeniously designed to fine-tune the model's policy, which, in this context, basically refers to how the model generates text, how it chooses words, constructs sentences, shapes its overall style.
Its strategy for generating responses.
Right. PPO operates in iterative loops, a continuous cycle of improvement. In each iteration, first, we let the current version of the language model generate a large set of outputs for various prompts or questions. Second, we use the reward model to assign a numerical reward score to each of those generated outputs. This gives us an immediate objective idea of how good each one is according to the learned human preferences.
So generate, then score with the reward model.
Exactly. Then, based on these reward scores, the PPO algorithm updates the language model's policy. Crucially, it adjusts the policy to increase the likelihood of producing outputs that previously earned high reward scores.
Trying to get more of the good stuff.
Right. This update process uses gradient descent, similar to the gradient descent we discussed for minimizing loss, but instead of moving downhill to minimize error, it actively moves uphill to maximize the reward.
Climbing the reward mountain.
Nice analogy. The proximal aspect of PPO is a smart design choice. It limits how much the policy can change in a single iteration.
Why limit the change?
It makes the training process much more stable. It prevents the model from making drastic, potentially destabilizing alterations to its behavior in one go. Keeps the updates smooth and controlled.
Ah, avoids breaking things while trying to improve them.
Exactly. We find PPO to be an incredibly efficient and reliable reinforcement learning algorithm, and it works particularly well for fine-tuning large language models with human feedback at scale.
You're exactly right. RLHF training is definitely not a one-time task. It's fundamentally an iterative process, a continuous loop of generation, evaluation, and tuning. We begin with the language model after it's already undergone supervised fine-tuning, and then we seamlessly transition into this RLHF loop.
So generate, evaluate, tune, repeat.
That's the cycle. First, the main language model generates new outputs for fresh prompts. Second, the reward model, our automated judge, scores these outputs and provides the reward signal. Third, using these rewards, the PPO algorithm meticulously updates and improves the main language model's policy, making it more likely to generate high reward outputs next time.
And each time around the loop, the model gets slightly better.
Correct. After completing one loop, we return to step 1, but now, importantly, we're working with a slightly improved language model. We repeat this entire loop many, many times over countless iterations. With each successive iteration, the model's policy becomes increasingly adept at generating outputs that achieve high reward scores.
And the result is a model that's more helpful, harmless, truthful.
As a direct result, yes. The model produces outputs that align ever more closely with human preferences, consistently becoming more helpful, harmless, and truthful. Because that's what the reward model, trained on human judgments, is rewarding it for. This iterative loop allows us to refine the model's behavior in a sophisticated way, making it more useful and aligned with the nuanced expectations of real-world applications.
And you can keep doing this as you get more human feedback.
Absolutely. Since it's a continuous process, we can refine the model even further as more human feedback is collected and as improvements are made to both the reward models themselves and the underlying PPO algorithm. It's an ongoing alignment process.
Fascinating. Okay, that covers the core training stages. What about the sheer scale of these things? Section 4, scaling up in future directions, bigger models, and new ideas. When it comes to deep learning, especially with language models, the undeniable trend seems to be that bigger is better, at least up to a point we haven't reached yet, maybe. Models are becoming larger and larger in terms of the number of parameters, those internal weights and biases. Millions, then billions, and now models with trillions of parameters are being developed.
Trillions, the scale is just mind-boggling.
It really is. So why do bigger models seem to perform better? What does scale actually buy you?
There are several compelling reasons. First, just raw capacity. Larger models simply possess more capacity to store information, giving them a greater ability to learn from truly vast amounts of data. More parameters means more memory, essentially. Also, with more parameters, the model can approximate more complex functions. It can capture finer nuances of language, represent a much broader range of world knowledge encoded in the data.
So, better representation, more knowledge.
Yeah.
But isn't there something else, this idea of emergence?
Yes, emergence. That's where things get really fascinating. Something truly remarkable happens when model sizes are scaled up dramatically. New, unexpected abilities seem to spontaneously emerge in these very large models. Abilities that weren't explicitly programmed, directly trained for, or even fully understood initially.
But what kind of abilities?
A prime example is in-context learning. You can provide just a few examples of a task directly within the prompt itself, like translate English to French, see otter loutre de mer, cheese fromage, d, and then you give it a new input to translate, like butter hag.
And the large model can just do it.
Yeah.
Based only on those examples in the prompt.
Surprisingly, often yes. It can translate correctly based solely on those few examples without needing specific fine-tuning for translation. Smaller models struggle significantly with this or fail entirely.
That's wild. It learns the task on the fly from the prompt.
It seems like it. This in-context learning isn't just a party trick. It fundamentally changes how we interact with AI. Instead of constantly retraining models for new tasks, we can now prompt engineer them on the fly.
Which makes them incredibly versatile, but maybe also harder to predict.
That's the trade-off. Emergence remains an active research topic, and it's not fully clear why it happens. Our best guess. With massive scale, the model learns a very general, powerful representation of language and knowledge that it can adapt flexibly based on just a few examples.
So it's not just quantity, it's a qualitative change.
Exactly. Millions, billions, trillions of parameters. These aren't just bigger numbers. They seem to represent qualitatively different systems with fundamentally new, emergent abilities. Now, while larger models boast more parameters and capabilities, they are also monumentally more computationally expensive, both to train and even just to use.
Right. The cost must be astronomical.
It is. Training models with trillions of parameters demands truly massive computing power. We're talking hundreds or even thousands of high-performance GPUs working together continuously for weeks, maybe months.
Just for one training run.
For one large model pre-training run, yes. And even using these models for inference, like generating text for your query, becomes significantly more resource-intensive, slower, and costlier for larger models. Managing the inference budget is a huge practical consideration.
So how do you train these monsters? You can't fit 1 trillion parameters on one GPU.
Definitely not. We rely on highly sophisticated distributed training techniques. For example, data parallelism.
Splitting the data across GPUs.
Right. The training data is intelligently split across multiple GPUs. Each GPU processes a portion, calculates gradients, and then the gradients are efficiently combined to update the model. But when the model itself is too large to fit entirely on one GPU's memory, which happens with these huge models, we employ model parallelism.
Splitting the model across GPUs.
Exactly. The model's architecture itself is split. Different GPUs handle different layers or parts of layers. This requires constant, highly optimized communication between the GPUs during the entire training process. It's incredibly complex.
Sounds like a massive engineering headache.
It is. Developing efficient distributed training systems is a monumental engineering challenge. It requires specialized hardware GPUs, Google's TPUs, and advanced software libraries meticulously optimized for distributed computation and communication. The sheer infrastructure costs are so astronomically high that realistically, only very large companies or extremely well-funded research labs can afford to train these state-of-the-art models from scratch.
Which raises questions about access, right? Democratization of AI.
Absolutely. It's a significant concern about accessibility and equity. This underscores the critical need for continued research into making powerful AI more efficient. We need more efficient architectures, maybe sparse models that require fewer computations, better model compression techniques, anything to reduce the resource demands.
The goal being to make powerful models more accessible without needing a nation-state's budget.
Precisely, making them more deployable and usable for a wider range of people and organizations.
Okay, so efficiency is key. What about fundamentally new architectures or ideas beyond just making transformers bigger or more efficient? Section 4.2. Architectural innovations and future paths. New research and ideas. The transformer architecture, especially self-attention, is incredibly powerful, as we've discussed. It revolutionized the field. However, it also comes with that significant computational cost. The complexity of standard self-attention is quadratic with sequence length ON2.
Yeah, quadratic complexity doesn't scale well.
Right. If you double the length of your input text, the compute cost quadruples. For tasks involving very long sequences, whole documents, long conversations, books, standard self-attention quickly becomes a major bottleneck. Speed and memory both suffer.
It hits a wall pretty fast with long contexts.
So, to address the scalability challenge, researchers are delving into sparse attention techniques. What's the core idea there?
The core idea is to reduce the computational cost by having each word attend to only a subset of other words selectively, rather than attending to every single other word like standard self-attention does.
So instead of every word looking at every other word, it only looks at a few important ones.
Something like that. This strategic reduction in connections results in sparse connections instead of the dense, fully connected attention we normally see. Less calculation needed. There are various methods for achieving this. Using fixed patterns of sparsity, allowing the model to learn its own sparsity patterns, employing clever approximations to the full attention calculation.
Are there models using this already?
Oh, yes. Examples include sparse transformers, longformer, reformer, among others. These methods often involve advanced underlying techniques like using sparse matrix math for efficiency, or applying things like locality-sensitive hashing, LSH, to quickly identify relevant words without comparing every single pair.
And the goal is similar performance, but cheaper.
That's the hope. Achieve performance comparable to full attention, but with significantly lower computational costs, especially crucial for handling much longer sequences. Making transformers more efficient and scalable for truly extensive inputs is absolutely vital for their continued evolution. The transformer architecture is currently dominant, no doubt. Language models, even vision models now. But is it the final answer? I really don't think so.
You think something else might come along?
Research is a dynamic field. It constantly explores alternatives, looks for new, fundamentally different ways to build these networks. When I think about beyond transformers, I see many exciting directions being explored.
Like what?
Well, for example, recurrent neural networks, RNNs, they were widely used before transformers took over. Their sequential processing nature might still be incredibly useful for certain tasks, especially with time series data or audio. There's also active research into cleverly combining ideas from RNNs and transformers trying to get the best of both worlds.
Interesting. What else?
Convolutions, often associated with image processing, are still used in some language models, maybe for character-level processing or alongside transformers for specific benefits. Even within attention itself, researchers are constantly studying variations. Linear attention, different ways to calculate weights, trying to make it more flexible or efficient.
So tweaking the current paradigm.
Yes, but also bigger shifts. Another approach I find particularly intriguing is the mixture of experts architecture.
Mixture of experts, like a committee.
Kind of. Instead of one monolithic, massive model, the system comprises a collection of smaller, specialized expert models. Each is trained to excel in a particular subtask or domain. These experts then collaborate, and their outputs are intelligently combined by a gating mechanism. It allows the overall system to handle a broader range of tasks with potentially greater efficiency.
That sounds promising.
It is. Then you have things like graph neural networks, GNNs. These models represent language or knowledge as a graph nodes and edges, allowing the network to process highly structured information in a different way. And looking further out, there's emerging interest in completely different paradigms. Neuromorphic computing, mimicking the brain's structure. Even quantum computing, though that's still pretty far off for practical AI.
Quantum AI, wow.
Yeah, distant future. But researchers are starting to think about how these entirely new paradigms might be used. Moving beyond today's conventional neural networks, research is always advancing. While transformers are incredibly powerful now, I firmly believe future architectures and AI models may look very different. The field is constantly evolving, new ideas emerge all the time. That's what makes it so incredibly exciting.
It certainly sounds like it. Constant change. Which brings us to maybe a final reflection. Concluding remarks? Still a long way to go. Many open problems. After going through all these intricate details, the data, the architectures, the training, the scaling, it's impossible not to be genuinely impressed by what these deep learning models can achieve. Generating text that feels human, answering complex questions, translating languages instantly. It's remarkable.
The progress has been staggering, truly.
But it's absolutely crucial to remind ourselves that despite these remarkable feats, deep learning is far from perfect. There are significant limitations, unresolved problems, many challenges still ahead.
Definitely not solved science yet.
One major issue is still interpretability, the why. It's incredibly difficult to truly understand the internal workings of these large networks. They're still, to a significant extent, black boxes. Even if you open the box and look at the billions of numbers, making sense of why it made a specific decision is no easy task.
Yeah, tracing a decision back through trillions of parameters is hard.
We desperately need better tools and methods to understand how these models make decisions, what knowledge they've truly learned, and crucially, how to debug and improve them systematically, rather than just relying on trial and error.
Agreed. Explainability is a huge challenge.
Another challenge is robustness. These models can be surprisingly fragile. Even small, maybe imperceptible changes in input or carefully crafted adversarial attacks can easily mislead them. They can give completely wrong answers with very high confidence.
Because they don't truly understand in a human sense. They're recognizing incredibly complex statistical patterns, disrupt those patterns slightly, and they can fail unexpectedly.
Right. And then there's the pervasive issue of bias. Models trained on vast amounts of real-world data inevitably inherit the biases present in that data, reflecting societal biases about gender, race, culture.
Garbage in, garbage out. Or rather, bias in, bias out.
Exactly. And they can amplify these biases in their outputs, potentially leading to unfair, discriminatory, or ethically questionable outcomes, even unintentionally.
A major ethical concern.
It really is. It's crucial to develop robust methods to detect and mitigate these biases, both in the data we feed them and in the models themselves, to ensure AI systems are fair and more equitable. Interpretability, robustness, bias. These are just a few hurdles. Deep learning has progressed astonishingly fast, but it's still far from solved. It needs immense further research, innovation, and a deeper focus on the ethical and societal implications.
Absolutely. And there's one more point worth considering related to that. In this field, a lot of the breathtaking progress we've seen is driven by engineering and practical results, often following a does it work philosophy.
Build bigger, train on more data, check the benchmark scores.
Pretty much. Build a bigger model, train it on more data, check if it improves performance. If yes, great. Publish the paper, move on to the next, even bigger model. However, I've often observed that theoretical understanding in deep learning frequently lags behind these rapid engineering advancements.
The theory hasn't caught up with the practice.
Often, no. While we can consistently build these truly amazing systems, like large language models capable of genuinely impressive feats, we often find ourselves grappling with why they work so incredibly well. What are the truly fundamental underlying principles? What are their inherent limits? The theory is still evolving, not as comprehensively developed as the engineering practices.
So there's a gap, a chasm, as you put in the outline.
Yes, I think there's a significant gap, a chasm, between practical engineering and deep theoretical understanding. Now, this isn't necessarily bad engineering progress is vital, but bridging that gap will likely be absolutely crucial in the long run to create more robust, more reliable, and ultimately perhaps genuinely intelligent AI systems.
We need the theory to catch up.
I firmly believe we'll need a much deeper, more fundamental theoretical understanding. This would help guide engineering practices in a more principled, less purely empirical way. I suspect the next truly big leap in AI might very well require more rigorous theory, more advanced mathematics, more foundational work.
Interesting perspective.
That said, I recognize we're still in a phase of incredibly rapid engineering-driven progress. Right now, I see us learning intensely by doing, fixing problems as they arise, gradually improving our understanding. It's an exhilarating time. So much happening, so much to learn and discover every day. But I'm also keenly aware of the inherent uncertainty, the many unknowns still hidden inside what we still sometimes call the black box of deep learning.
A perfect place to leave it for today. As we continue to push the boundaries of what these systems can do, it really invites us, and you listening, to consider how might a truly deep understanding of the why and how behind current AI capabilities fundamentally reshape not just how we build future systems, but also how we interact with and perhaps crucially trust them in our daily lives. And maybe a final thought to ponder. If we truly unlock the black box, what new ethical and philosophical questions will emerge about the very nature of intelligence itself? Something for you to think about, perhaps, until our next deep dive.